So we restart the presentation from the morning, which had to deal, I was showing to you basic features of what we believe was the burst and the evolution of our universe undergoing from the Big Bang, even if we have no idea of what the Big Bang itself could be. We have seen how the evolution was undergoing, starting from a period which presumably what we imagine could have been inflation, so a very fast acceleration in the first instance, like 10 to minus 35 seconds, when the universe grew by something like 60 orders of magnitude. In order to explain this, the uniformity of far remote directions in the universe, which seem to be so uniform. So uniformity of the universe, it's explained, or at least the trial to explain it, it's related with this inflation theory. We have seen that afterwards, the universe, which was born as a collection of particles and antiparticles, undergo annihilation. Part of the matter survived due to the asymmetry between matter and antimatter. And then after it clustered in first in particles like protons and neutrons, which themselves created nuclei, the smallest nuclei, like hydrogen and helium, which then created some atoms when radiation decoupled from the matter, 300,000 years after the Big Bang. Afterwards, structure started to get burst. This is more or less an image of the universe around 1 billion light years across, where we can see, however, that there are huge voids, so regions which are empty of matter, while the other regions are full of super galaxies, superclusters of galaxies. And we believe that these structures were generated in the first instant of the instance of the Big Bang due to the quantum fluctuations in that period. So this is the latest picture we have. Well, it's a collection of various information. If we put together information coming from satellites, from telescopes and radio telescopes, we have commented a little bit saying that since we stay in the middle, this might be an indication that the universe we see here might not be the whole universe, which could contain ours as a small portion, and I will come back to this when we speak about the parallel universes. However, one of the main ingredients of the universe are the galaxies. The galaxies, which are under different type of shapes. The most common ones are the spiral galaxies. Ours, it's a spiral galaxy, so they contain usually quite a huge number of stars, like ours, 100 billions of stars, and they have different kind of shapes with arms which might be of various numbers. And a part of this, we have elliptical galaxies, which some of them might be the oldest one in the universe. They might have this shape of elliptical galaxies, while others are lens-type galaxies, which are a bit more rare than the other ones. And finally, there are irregular-shaped galaxies, like the Large Magellanic Cloud. Usually, these galaxies, either they are very young or they are very small, in the sense that if the number of stars is at the order of thousands, and this is again a problem, how big should be the number of stars to can call a star group a galaxy? Now we believe that usually 1,000 stars are kind of enough to define an object as being a kind of a very small galaxy. In this case, you don't really expect that they have a very regular shape, and then you have these cluster galaxies like the Large Magellanic Cloud. The basic ingredient of the galaxies, at least from what we know from the visible matter, I don't comment, or I will comment later on about the dark matter, are the stars. So the stars are the main actors in the universe. And we see here a very basic mechanism which keeps the star alive. So a star maintains its life as long as there is an equilibrium of various type of forces. On one side, there is the gravity, which pulls the matter to become more and more dense and to eventually contract towards something which might become, and we will see sometimes it does become, a black hole. So gravity is one force which pulls things together that would like to aggregate the matter in an eventually unique point. On the other side, there are forces which oppose to gravity, which are the nuclear reactions. So inside a star undergo nuclear fusion reactions, where the smallest nuclei, like hydrogen and helium, they set together, they join each other to create bigger and bigger nuclei. We will see that there is a limit. They undergo reactions until iron, so they don't go beyond iron, and we will see why. And as long as there is any reaction, fusion reaction inside a star, since the fusion of smaller nuclei up to iron undergoes by having energy in the balance of energy, there is energy left over, so energy is created, it's not created, but the energy transforms in a kinetic energy. The mass of the initial ingredients can transform in kinetic energy, which kicks, so wants to push each other, the particles inside the nucleus, which means that it opposes to gravity. So the fact that when the two small nuclei fuses in a bigger one, part of the mass is transformed in energy. In the end, this is kinetic energy, which opposes to the gravity. So as long as we have something to still give fuel to the star, so to undergo nuclear reaction, the star remains alive. Which means that in principle, if we are able to know how the nuclear reaction go, and we know this from our accelerators and from our cyclotrons or various type of accelerators, we have studied this reaction in our laboratories. So since we know how they go and which is their reaction rate, we might estimate the life cycle of a star and its life period by knowing its mass. This is a kind of a more precise view of what I have shown to you before. So in the inner core of the star, where the pressure is very high, where the temperature is extremely high, there are tens of millions of degrees, they undergo nuclear fusion reaction, intensive nuclear fusion reaction. As far as you go from the center, the star gets colder. We have seen that for our star, we start with 10, 20 million degrees and we arrive to 5,000 degrees. So the star gets colder and it evolves having a certain type of color. We will see that the color depends on the mass of the star, because the fuel, so the number of reactions, the rate of these reactions depend on its mass. So it goes and it delivers what we see, for example, in our sun. So the life of a star depends on these factors, which are on one side the gravity, on the other side the nuclear reactions, and as long as they still balance each other, the star keeps being a star which is alive. These are the typical nuclear reaction fusion reactions, the simplest one, undergoing in a star. So initially a star, it's a collection of nuclei, basically hydrogen. So not only hydrogen, but basically hydrogen, so protons actually. So the protons join together in a deuteron, so little bit higher nucleus, a deuteron, and then this reaction goes together with the delivery of a positron and a neutrino. Neutrino, it's a very interesting particle, not only because we still don't know its mass, we don't, but it's very interesting because in this context of life of a star, since neutrino does not interact or interacts very, very weakly with the rest of the star matter, it succeeds to get out of the star. gets out with a lot of energy, kinetic energy, so it helps the star somehow to cool down. So not all the energy trapped and created in the core stays there, make the star, for example, blow away, but the neutrino contributes to the cooling process of the star. It drags energy away. So whenever we have a process which delivers neutrino, this contributes to the cooling of the star, or at least to the equilibrium processes which go in a star. The study of the neutrino, by this point of view, it's very, very important, because it helps us to understand better what undergoes into a star, and the neutrino coming from our sun were studied for a long time. They are still studied, for example, in Gran Sasso Laboratory. There are experiments like Borexino, which are delivering a lot of interesting data related with the sun neutrino. There are different types of processes. Of course, if you put a deuteron together with a proton, you get a heavier nucleus like helium-3 and so on and so forth. You can get helium-4, you can get carbon, you can get oxygen, and you can get, in this way, nuclei up to iron. I want you to notice that each time this reaction happens, they can happen only because the energy, when I say energy, it means mass plus kinetic energy, so total energy. They can undergo only because the total energy in the beginning, which it's equal, of course, with the total energy in the end, but the total energy in the beginning is higher than the mass of the generated nucleus. So part of the energy remains here as neutrino and positron. Here, again, series of neutrinos and other particles. But these reactions are occurring sorry, as long as we have a reaction, a fusion reaction, for which the mass of the final nucleus is smaller than the sum of the mass of the initial nuclei. So as long as we don't need to give energy to the initial nuclei, we can have this spontaneous, at least in the sun, kind of spontaneous nuclear fusion reactions. Of course that if the star is big or small, this matters, because the rate of the reactions, the number of the reactions undergoing into a star depends on their volume. Bigger is the star, bigger its volume, more and more nuclear reactions undergo in their inner core. And this makes so, this is the very important Hertzsprung-Russell diagram, which sets and classifies the stars according to their size on which it depends both their temperature, be aware that the temperature increases in this direction, as well as the luminosity, how brilliant is that star. So we can see here that the big stars are they emit a lot of light, a lot of energy. They are very brilliant. Their luminosity is high, while smaller stars, they get fainter and fainter, and their surface temperature gets lower and lower. So our sun, for example, stays more or less in the middle. It's not quite a big star. It's kind of a medium or even smaller than medium size, which has a color on surface corresponding more or less to this temperature, which is some thousands, 5,000–6,000 degrees. The bigger star, they get a color class which define them as blue stars, while the smaller ones are red and faint red stars. Now, one question. What do you believe, that a big star lives longer, shorter? How is the life of a big star with respect to the life of a small star? It's shorter, right. In spite of the fact that one might be, one might believe that since it's bigger and bigger, this means that it has more hydrogen inside, so more things to burn, which might induce us to believe that if it's bigger, it lives longer. This, in the end, it's not true. It's not true because, of course, it has more hydrogen inside, but it has to burn more hydrogen, and this goes with the volume. So to maintain, to oppose the gravity which would pull it inside, it has to, in the end, to burn more hydrogen, which makes so that the number of reactions per second are much bigger than the number of reactions into a small star, and in the end it happens that a very big star lives much shorter than a small star. Fortunately for us, our sun is not so big as a star. Fortunately, because the life cycle of our sun, it's around 10 billion years. We are presently in the half period of sun's life, so the sun will die out after 5 billion years. While there are big, enormous stars, the giant stars, which can live even some million years. So they live very short. Of course, that if our sun would have been such type of star, we couldn't be here because life has no time to evolve and to develop in only a few million years. By this point of view, when one looks for life in the universe, it's more tempted to look for it in the stars which are small, because some of them, smaller than our sun, might even live 100 billion years. So it's somehow more probable of course, that then the planet should be closer to the sun and so on and so on. But it's more probable to have time to develop near a small star than near a very, very big and powerful star, which lives far too short. What happens when a star exhausted its nuclear fuel? So the star usually dies out. The way in which a star dies differs. It's different accordingly to its initial mass. I show you here an example. We have seen already some elements from Massimo Ferrario when he spoke about the radiation emitted due to the intense magnetic field. This is a pulsar. So in the end, this supernova delivers a neutron star. In this case, this is what remains. A neutron star with an intense magnetic field which delivers a lot of radiation. So when a star dies, what happens to it depends on how big it was. So by this point of view, the stars are very predictable. So we can know what will happen with a star as long as we know its mass. And let's see what can happen. So what's the life of a star? Not all of them are ending up in a supernova and delivering a neutron star. This is what I showed you before. So this is one example. So this happens, for example, if a star has the initial mass something like 1.5 up to 4 times the mass of our sun. So when a star is so big, in between few times the sun, when it does not have anything to oppose gravity anymore, because all the nuclear reaction which could go undergone, so there is nothing which can fuse anymore, nothing to oppose gravity. So the star becomes a red giant, so starts exploding, and it triggers what is called a supernova. Main part of the matter is dragged away in the explosion, so main part of the nuclear matter like carbon, oxygen, and so on are blown apart. That's why we are stardust in real sense of the word, because our nuclei were forged inside the heart of a star. And what remains, at least in this case, whatever was not blown away, it collapses. It undergoes a gravitational collapse, and in this case delivers a neutron stars. But I repeat, it's not always like this. This is the final evolution of a star when it exhausted, of a star bigger than ours, when it exhausted the nuclear fuel. So we see that all elements up to iron are created in the star, so it has a heart of iron. Then other elements are present here, and there are many, so magnesium, neon, oxygen, carbon, which for life it's fundamental, it's carbon-based. I show you here while it stops at iron. while in order to create other elements, we need other mechanisms. So here you can see that when you start, this is the energy per nucleon inside various types of nuclei. So the binding energies in the nuclei for various kind of nuclei. Binding energy per nucleon, sorry. So you see that the small elements are having a lot of binding energy, while the iron has a kind of smaller one. So which means that what I told you before, if you start with hydrogen and go towards iron, what happens is that this reaction undergo with releasing energy in the end. So you can release energy in form of kinetic energy of the final products. If you want to go beyond iron, so if you want to create, for example, lead or uranium, you need to do the opposite. So you need to give a lot of energy to the initial nuclei which collide. For example, you have an iron and an oxygen. You want to put them together. In order to succeed to put them together, you have to give them energy from outside. So it's not enough to keep them together and they fuse and they give birth to a bigger nuclei. In this case, you have to strongly kick them and to deliver the bigger nuclei. And since we still do have uranium and lead, we can wonder where they come from. I told you that they are not created inside the star, so where they come from? They are not coming from the Big Bang. They are coming from the supernova. So when a star explodes, when this star explodes, it does not have any more nuclear reactions because it arrived to iron. It explodes. And what happens in this case is that these elements like oxygen, carbon, magnesium, and iron are dragged away with huge energy in the explosion, and they can suffer nuclear fusion reaction while blowing apart. So the nuclear fusion which creates lead and uranium happens in the moment in which the star explodes. So the lead, uranium, thorium, heavier elements are, all of them are coming from supernova explosion. So our body is created not only from the reactions which occur in a star, in the inner core of the star, but moreover, part of our elements heavier than iron are coming from fusions which can only occur in a supernova explosion, because this gives energy to the smaller nuclei to fuse together and to deliver bigger and bigger nuclei. Now I don't want to spend time on this, but one might wonder in the Mendeleev table how many nuclei there are. We know that, for example, there are more than 100, something like 120. Is this all? Are there nuclei which we didn't discover? Did someone of you heard that some weeks ago the Japanese physicists succeeded to artificially create 4 new elements? So 4 new nuclei, which for the moment do not have a definitive, final name, which are heavy nuclei, of course. They succeeded to do this in accelerators by chemical and physical methods. And this again makes us to wonder, are there even heavier nuclei? The nuclear physics says that if you do the calculations from what we know today, that there are heavier nuclei. They are the so-called island of stabilities. So nuclei which should be very heavy, twice heavier, for example, or even more than the nuclei we know, only that they are not in a continuous with our nuclei. So we should somehow be clever enough to create them by melting together 2 already big nuclei if we are able to. So this is a very interesting research sector. It's a kind of a nuclear chemistry which makes us to wonder how heavy a nucleus.
But if these atoms are stable, theoretically, why we haven't found them in nature?
There are 2 possible answers. One is that their concentration is so small that it's impossible to see them. So there might be, I don't know, 10 to minus 25 on all Earth grams. So it's difficult to see them if they are any. And the other answer is that the remnants of the supernova in our local cluster did not succeed to create that type of heavy nuclei. But this is a very interesting and very alive topic in the nuclear physics and in astrophysics, because they go together. So the distribution of the elements, it's very interesting, and it's being studied not only on Earth, because what we see on Earth and the relative composition of Earth, it's not the same on the Moon. It's not the same on Mars. So it could be that this tells us something about how this object got burst, but it's a good question. Why didn't we find them? Probably because their concentration is so small, or they are not yet existent. The supernova did not succeed to trigger that kind of reactions. So what happens then with the life of a star? As I told you that, so before the star, how the star born? The star is born when a kind of a cloud, interstellar cloud matter, starts to gather together under gravitational attraction. When the matter arrived to be in a high density, high concentration, it starts to deliver a protostar. So the protostar is not yet quite a star, but some fusion reaction starts to get in action, and this attracts somehow more and more matter till at some point a massive star is delivered. The star then lives its own lifetime, and we have seen that bigger it is, shorter it lives. And at some point, when there is no any more fuel, the star explodes. The star can explode mildly or in a very violent way. Here, for example, it's a very violent one, so I took a massive star. So when a massive star arrives to die, initially it creates a pulsating yellow giant, which then gets an explosion, which is extremely impressive, arriving in the end to a supernova explosion passing through the red giant phase. And after lots of material, actually almost all, it's blown away, what it remains is either a black hole or a neutron star. Whether it's a black hole or a neutron star, it depends on the initial mass of the star. If the initial mass is sometimes bigger than our sun, like I told you, 1.5, 3 times our sun mass, it delivers a neutron star. If the mass of the initial star is kind of 10 times, let's say, our sun, what remains, it's a black hole, in the sense that the gravitational collapse of the remaining part of the fragment, which was not dragged away by the supernova explosion, cannot hold the gravitational collapse in a form of known matter, like the neutron star, but it continues and it undergoes a collapse which delivers these mysterious objects, which are called the black holes. What about our sun? So our sun, it's a kind of a medium towards smaller type of stars, and what will happen with it? In the case of our sun, after it gets burst, after processes which aggregates interstellar cloud and dust, it lives kind of 10 billion years. Now I repeat, we are more or less in the middle of its life. And when the sun will end up its life in 5 billion years, more or less by now, it will explode. But its explosion will never be in the form of a supernova. So the explosion is more mild. It will become a red giant. So it will start to be a red giant, will pass through various pulsating phases. And in the end, what will happen, we will see that in the phase of red giant, this explosion, it's involved a lot of space regions. So in this phase, this red giant will arrive up to Earth orbit. So even if one can assume that humanity or whomever will be still there in 5 billion years by now, they will have to do something, because the sun will burn everything. The red giant phase of the sun will burn our Earth. And what remains after, it's again a central part which did not blow away under this kind of explosion, and in the end it remains a kind of a white dwarf. The white dwarf, it's a kind of a rock, a huge rock which remains cold and without nuclear reaction, remains fluctuating in the universe until eventually collides with some other objects. So it's not so spectacular as a supernova. This is the meaning of we are stardust, the deep meaning in the sense that it's not only imagination, but it's really reality. In two ways, elements up to iron are forged directly inside the stars, while heavier elements than iron are created during the supernova explosion. What will happen? We have seen that evolution starting from Big Bang up to present days, it's a universe which is expanding, not only expanding, but it's expanding in an accelerated way. And we might wonder what will happen in the future related to this model, so cosmological models, not only from the past to the present, this is Big Bang, but from the present to, I don't know, I hardly can call it infinity, because infinity is something very, very difficult to imagine, at least to me. So one might, if we extrapolate what happens today, we might imagine that the expansion will continue in an accelerated way forever. Somehow this is quite frightening, because if this is true, it will happen that sooner or later, depending on if the acceleration will continue, you will look around, not you, whomever might be here somewhere, you look around and you see nothing, because all objects were flying away due to the universe which is expanding too fast. So there will be no galaxies, there will be no objects which succeed to aggregate together. And it's quite challenging to imagine what kind of cosmology, if any, eventual creatures living in that age might invent. On the other side, one might imagine that somehow the acceleration will be stopped and either the universe remain more or less stable, or it goes an expansion which is more mild, or even, why not, expansion can invert the direction, and it can go towards a recollapsing universe, towards the opposite of the Big Bang, which is the so-called Big Crunch. This might somehow answer a few questions, because if one imagines a scenario like this, you can think that whatever comes here then starts again here. So it's a kind of oscillatory universe where the birth of a new universe is actually the end of a different universe. But for the moment, we don't have elements to believe any of this scenario, because we don't know ingredient features of the universe, the dark sector. What is the dark energy and what is the dark matter? While yesterday you have had already from Matteo some elements, some possible candidates for dark matter in the form of the supersymmetric particles, I will tell you something more by Friday when we will discuss 7 big open questions about the modern physics. So, however, this is what I wanted to repeat to you, that since apparently we only know, and the picture of the universe I showed to you when I insisted on the fact that that image of the universe is based only on the electromagnetic information, because the electromagnetic information relates to 4% of our universe. The rest is the dark sector, and that's apparently, unless we don't mistake something badly. One might always be that one might mistake something badly, but if we don't do any sort of catastrophic mistake in our laws describing the universe, there is a huge portion of the universe, the main one, that we still don't know what it is made of. And that means that the cosmology in the future might suffer different scenario, might be better understood by understanding better this dark sector. Now some words about parallel universes. I wanted to divert you, since now it's late afternoon, just to give you some overview of different classes of parallel universes, because they amuse myself. So the first, it's a very kind of trivial parallel universe classes. If we can imagine that the universe is really infinite, one can then believe that what I've showed to you, that we are in the middle, the image where I told you, this is our visible universe. The universe might be a lot bigger. Now, there is one thing to say here. Even if the universe is much bigger, the fact that we don't see it bigger, it's not a limitation in our present-day technology. It's only due to the fact that the universe was born 13 billion years ago. Of course, that if there is some star here which is distant from us, something like 50 billion light years, the star emitted a light which did not yet have time to arrive up to us. So if the universe is bigger, at least staying to our present-day physics, there is no way to know it. And it's not a limitation of technology. It's a limitation due to the fact that the universe was born 13 billion years ago. In 10 billion years, by now, the known universe will be 10 billion light years bigger, because the light from farther stars will have time to reach us. Now the light from here arrived here, for example. It might reach us in many, many times from now. So we can imagine easily that the universe, in fact, even if we don't know it, and even if there is no way to know it staying to today's physics, it's bigger, eventually infinite. So galaxies might exist beyond the horizon, and their light had no time to reach us. Then the simplest thing you can imagine, that there are kind of parallel in the sense that they are there, but they didn't yet, the light did not yet reach us. So the sphere which I showed you can be repeated. Of course, now I draw sphere here, but in fact, here is matter as well. It's only a representation. So universe can be kind of even infinite. So this kind of sphere repeats itself many, many, many times, and in many, many ways. Now there is very interesting argument related to this, and it goes as follows. Let me arrive here. That if in all these universes parallel to ours, beyond ours, physics is the same as in ours, and the number of particles is the same as in ours that we know, it's easy to imagine that in an infinite universe, if the number of particles is finite, you will have all sort of arrangement of these particles, but sooner or later, you will repeat yourself. So if you have, for example, a collection of balls, white and black, only two of them, it's easy to imagine how many times you have to extract these balls if they are equally distributed in order to get the same configuration. So it's an easy, trivial problem of combinations. So if the universe is infinite, and if the numbers of particles, if the types of particles are finite, you can imagine that sooner or later you will have a situation which is identical to the starting one. What does it mean? It means that maybe somewhere in the bigger universe, it might be that somebody else equally to us stays equally in the same place and does exactly what we do. In other of these universes, somebody equally to us does something completely different. So this is combinatorial in an infinite universe. Of course, these are speculations. There is no way to know it unless we discover either signals which go faster than light or some kind of strange entanglements from quantum mechanics which might entangle all these universes. But again, these are speculations, so it goes under the quantum mechanics weirdness. So this is a class of a rather easy and trivial and quite understandable way to do parallel universes. There is then another type of parallel universes, rather similar to the first class, but this assumes that the universe, the bigger universe, might be indeed infinite, but nobody grants to us that the physics, the type, and the number of particles, and even of space-time dimension, is the same in these other universes. So it might be that if ours, it's one of these, there are many others where, however, the physics is different. So this is a different sort of universe with respect to what I told you before. So it means that, for example, there might be worlds where are 6 dimensions, 6 space dimensions, or there are 6 forces or only 2, or many other particles or many other interactions. This is less trivial than the first universe, and this is only ours. The others might be completely different. Is there any theory or theoretical background to imagine this? Actually, there is a theoretical background which not only promotes the existence of this type of parallel universes, but even more, it requires this type of universes. It's the string theory. The string theory, which me as an experimentalist, I can debate on it because there is no way, at least presently, to experimentally check it, so we are quarreling, theoretician, experimentalist. However, the string theory has a kind of a gift in the sense that it eliminates the point from physics. It leaves it in the mathematical world. The point in physics, namely that presently we name fundamental elementary particles something which is structureless, it's a big problem in physics. It always has been. So if we imagine the quark as a point and electron as a point, one might wonder how the characteristics of this particle, like the mass, like spin, like charge, how do they stay on nothing, on a point? So one of the very appealing features of the string theory, it's not only this, the other one, maybe even more important, is that finally it succeeds to put gravity together with the other forces, with a price I'll tell you about. But one of the most appealing features of string theory is that it eliminates the point. Nothing is a point anymore. Particles are strings which vibrates, very small strings, 10 to minus 30 something centimeters. We can't see them. We have no lens going so far, and no accelerator can reach for the moment that smallness. I told you that this string not only vibrates, and that's nice because the particle is not zero. It has a dimension. It's a string which vibrates in 10 or 11 dimensional space. Why 10 or 11? Because rather magically, in that number of dimensions, gravity becomes mild force, and it becomes a force which is equal to the others, and one can quantize gravity. So that's another appealing feature of this string theory, which came in action. The problem is a problem and an opportunity, and the philosophy and not so much physics, at least not experimental-like, is that this type of theory, the string theory, the hope of the people who work on it was to demonstrate that our universe is that universe. And it's a big surprise, they actually proved that there are a class of equivalent string theories, not only one. There are M-class, M-type of theories, which generates 10 to the power 500 universes. So in string theory, there are genuine parallel universes. And unless you don't find an additional condition which cuts 10 to the 500 minus 1 hours, you have to accept somehow that other universes, parallel universes, with different physics, completely different number of dimensions, so very different from us, might exist somewhere. Even it's hard to say somewhere because one might say where. It's okay, parallel universes. So the string theory, it's a good candidate to make things even more complicated. Notice, however, that the first class of parallel universes are going well together with the second class of parallel universes. So our, as it is, might be infinite. So different kind of spheres can repeat. Moreover, our universe might be not the only one, but some others might exist. Maybe someday we will know whether string theory has any chance to describe indeed the universe, or it is only a fancy, complicated mathematical toy. That day did not yet arrive. Finally, another class of parallel universes, a bit more sophisticated, we go more and more sophisticated, it's related to the problem that Mauro was kind of discussing this morning, namely the superposition of states in quantum mechanics. So he told you that while in a macroscopic world, we have either the cat like that or the cat like that, but not superposition of states. In the particle world, you can have superposition of states. That's the famous Solvay Congress in 27, where the main figure in quantum mechanics are quoted there. You see here again Schrödinger, I will come back, but there are many other persons. And here we arrive at the famous Schrödinger cat. Sorry, the writing it's in Italian because I only knew that I have to do this talk afternoon yesterday evening, so part of the slides are still in Italian. But however, as I noticed, many of you do know about the Schrödinger cat. So Schrödinger cat, it's a paradox, was put forward by Schrödinger when he himself, together with Einstein, became rather unhappy of the way in which quantum mechanics developed. And they said and believed that there is something which is not yet fully understood in this theory. And he used this cat just to say that while if everybody accepts the microscopic weirdness, this microscopic weirdness can be transferred even to the microscopic world, and this might be rather shocking. And this is this cat, half alive, half dead. Of course, he used this just to impress more people. So it goes like this, that you have a nucleus, a radioactive nuclei, nitrogen-13, for example. We have a certain number of radioactive nuclei. The radioactivity, it's a probabilistic process thanks to quantum mechanics, which means that, for example, in 10 minutes, you have the probability 50% that some nuclei decay. When the nuclei decay, they trigger a hammer, and the hammer delivers a poison, and consequently, the cat is dead. So at the end of the process, after 10 minutes, if one asks, without opening the box, what about the cat? He said, the only thing you can say about the cat is half life, half dead. It's a superposition of state of life, half dead. And this happened in 80 years, from 80 years in the past. So since then, people do discuss, and there is not a well-accepted solution in the quantum community. So everybody, there are classes of groups who believe that this paradox points towards the fact that quantum physics, it's a limit theory of some other theories still to be discovered. Others believe that the world is like that and there is nothing else one can do apart accepting it. Others instead believe that this weird picture that you have half, so a superposition of macroscopic states. This is Einstein, it's the probabilistic aspect of quantum mechanics he didn't like. He said God doesn't play dice. And Bohr was telling him, don't tell to God what he needs to do. If he wants to play dice, leave him to play dice. So this is the eternal conflict in quantum mechanics. But there is an interpretation of quantum mechanics, a part of others, which relates to the parallel universes, the so-called many-world interpretation, which is a rather fancy theory. It's rather appealing intellectually or philosophically. Fortunately, it has no way to be proven, in the sense that this says that each time you do a measurement, and we have discussed what a measurement means, it does not necessarily need an observer. Whatever interaction with environment is, in fact, a measurement. So whenever you have a quantum process, and whenever there is a measurement in act, the universe kind of splits. It delivers many worlds. In one world, the cat is dead, and in the other world, the cat is alive. Of course that this triggers interpretation and wonders, like the most obvious one, where is the energy conservation? Is really the universe becoming twice, 4 times, and so on? So this goes with the conservation probability of the matter and energy. And this triggered enormous discussions, which arrived up to consciousness level, because somebody said, no, look, you solve all the problem if you believe that this happens only in the brain of the observer. I don't want to enter in detail, because this is not real physics in the classical sense of the word, even if it's very interesting itself. But however, one of the interpretations goes like many worlds. There are some others, like the last one, the collapse of the wave function, which says that the Schrödinger equation is an approximation of a different theory. Why I'm saying about this? Because I work on an experiment trying to find signals from a theory which goes beyond the Schrödinger equation in the Gran Sasso underground laboratory. And next days I will be happy to tell you if you want to know. So this is another type of kind of universe, parallel universe. Of course, that if you really want to, then there is another idea that there is no universe, not even one. So everything is a simulation. So forget about parallel of this, parallel of that, different physics. There is no universe. Everything is information. Everything is a huge computer computing. So this is a kind of a simulation theory. And it undergoes, there are theories which are saying that the universe actually is a simulation. So more or less, I finished here. I wanted only to give you a flavor, not only about Big Bang and theory and the cosmology, stars and evolution, but some kind of amusement of what this brings to if you really tackle with it in details. And if you think about the universe, about the known, observed universe, and about what could be beyond what we observe. Thank you very much. And I hope that some of you will be inspired and will study this maybe, if not in physics, however, will continue to stay tuned because it's really, really interesting.